Hi guys, it's Mrs. Harmison with your advanced chemistry notes for Chapter 19, Nuclear Chemistry. This lesson is about radioactive decay, which is when an atom loses part of its nucleus. Radioactive decay can happen spontaneously, when a nucleus decays without being bombarded with neutrons, or it can happen due to bombardment, which is when scientists hit an atom with a stream of neutrons in order to create a nuclear reaction. Nuclear fission occurs when a large nucleus splits into two smaller nuclides with somewhat similar masses and energy is released. Nuclear fusion is the combining of smaller atomic nuclei to form a heavier nucleus. A chain reaction happens when neutrons released during nuclear fission cause more fission to happen. These chain reactions can be really good when controlled, in the case of nuclear power plants, but they can be really dangerous when uncontrolled, in the case of nuclear weapons. A nuclide refers to the nucleus of an atom that we know how many protons and neutrons it's made of. A nucleon is something that exists in the nucleus, so protons and neutrons are nucleons. The half-life of a radioactive element is the amount of time it takes for half of the sample to decay.
If we had a radioactive sample that started with 2 grams of mass and it took 14 days for it to decay to only have 1 gram of mass, then we would say that its half-life was 14 days. And then in another 14 days, the mass of that radioactive sample would be 0.5 grams.
So you might wonder which elements are radioactive. This periodic table shows the radioactive elements. As you can see, they are mostly the bigger elements, and specifically, they are the elements that are past uranium. On the periodic table I gave you, the molar masses of the radioactive elements are in parentheses. Elements are elements with a larger atomic mass than uranium's, which is 92. They don't exist in nature except for trace amounts in uranium ores and when scientists create them by bombarding other elements with nuclear radiation. Here are the different types of radiation that we are going to talk about in this chapter. First of all, there's alpha particle radiation. Alpha particles are made up of helium nuclei, which means there's 2 protons and 2 neutrons in each alpha particle. Alpha is the least penetrating type of radiation. If you put it into an electric field, it will be attracted to the negatively charged plate. Alpha radiation usually occurs spontaneously. Beta particle radiation is made up of electrons. The electron has no mass and a negative charge. Electrons are more penetrating than alpha, but less than gamma radiation. Beta particles are negatively charged, so they're attracted to the positive plate in an electric field. And beta radiation also occurs spontaneously. Gamma rays are high energy electromagnetic radiation. They are not considered to be composed of particles. They are the most penetrating radiation. They're not affected by an electric field. And then a positron is another type of radiation. A positron is exactly like an electron in that it has no mass, but it has a positive 1 charge instead of a negative 1 charge. We're about to get started balancing nuclear equations, but I just wanted to remind you of a skill that we've already learned that's really important in order to be able to do this. You need to be able to determine how many protons and how many neutrons are in any given isotope of an element. To do that, you'll look at the atomic symbol. So this right here is lead-209. You would write its name like this, lead-209. This number down here is the atomic number, which tells us how many protons there are. So in this isotope, there are 82 protons. And as a reminder, those are the positively charged nucleons. This number up here is the mass number. The mass number is equal to the protons plus the neutrons. So that's the total number of nucleons. So in this isotope, if we wanted to figure out how many neutrons there were, we would take 209 minus 82 and determine that there are 127 neutrons. Writing a balanced nuclear equation is actually easier than the first type of balancing equations that we learned. All you have to do is make sure that the top numbers and the bottom numbers add up. So we're going to start with astatine 218. So you look on the periodic table and find the symbol for astatine, which is AT, and then the 218 is going to be the top number. And then we also have to find the atomic number on the periodic table for astatine, which in this case is 85. We have our arrow there, and any time that it says undergoes alpha emission or undergoes beta emission, that means that the alpha or the beta is going to be on the right side of the equation. It is being given off by the nucleus. So we have an alpha particle here, which an alpha particle is a helium nucleus, so 4 and 2. And then what we have to do is figure out what's going to go right here. We have to find a number to go here that adds up with 4 to get 218. So here we would put 214. We find a number to go here that adds to 2 to get 85. So we would put 83. And then we look up what element has 83 for an atomic number, and it turns out to be bismuth. So we put Bi. Now on OWL, when you're entering this, when you click in the box, there's an option to choose a template that has boxes that look like this, and that's the one that you need to choose, and it will let you type the numbers and the symbol right in there. All right, this one tells us that we're starting with polonium 218, and so we have to look on the periodic table and we find that polonium's atomic number is 84. It tells us that it's undergoing beta decay. In the decay process, the beta is going to be a product. Beta can be written like this or like this, so we'll put in this one. Then we need to figure out what's going to go here. We need something that adds up to 0 to get 218, so we put 218 up there. And we need something here that adds up to -1 to get 84, so we put 85, which is astatine's atomic number. All right, and this one, nitrogen 13, so we put N13. We look on the periodic table and find the atomic number of nitrogen, which is 7, decays by positron emission. So a positron is an electron that has a +1 charge instead of a -1 charge. So we are going to need to have 13 here because 13 plus 0 is 13, and 6 here because 6 plus 1 is 7. Then we would look up and see the atomic number 6 goes with carbon, so it would be carbon 13. In this example, gallium 74, which has an atomic number of 31, is going to undergo beta decay. So now this time we could put the beta in as 0, -1. What's going to result is going to have this top number is going to be 74. The bottom number is going to be 32. So we look up which element has an atomic number of 32 and see that it is germanium. So the product nuclide, that's this, has a name of germanium 74, and it has a symbol that looks like this. So again, you'll use the boxes in OWL and put that right in there. All right, on this one we have to add up the numbers on the top. So 210 plus 4 is 214, and then we add up the numbers on the bottom. 82 plus 2 is 84, which is polonium. So this is an example of fission. What's happening here is the isotope is being bombarded with a neutron, and then it's also producing more neutrons. And what this does is this allows for the possibility of a chain reaction. So these neutrons can then go bombard another isotope of uranium and create a chain reaction. So we need to figure out what isotope is going to go here. And again, we just have to make sure everything adds up. So 235 plus 1 is 236. So we need the top to add up to 236. So 236 minus 92 minus 2, because we take 2 times 1 to get the mass of 2 neutrons, gives us 142. So 142 is our top number here. And then to figure out the bottom number, down here we have 92 plus 0, which is 92. 38 plus 0 is 38. So we take 92 minus 38, and we get a bottom number of 54. That is xenon. In this case, the beginning isotope is being bombarded with an alpha particle, and we have to do the same thing, make it all add up. 13 plus 1 is 14 on the top, so we need this to add up to 14, so we need a 10 on the top. 7 plus 0 is 7, so we need this to add up to 7, so we need a 5 on the bottom. And boron is the element that has 5 as its atomic number. So there's our symbol.